Welcome everybody. In today's video we're having a look at the so-called quaternions, which are an extension of the complex numbers. We're not going into much detail or prove anything, but I just want you to know some interesting facts. It would be an excellent exercise to actually fill out the missing details by yourself. That's not hard, sometimes a bit tedious, but I strongly encourage you to do that. So, remember, when we went from the real numbers to the complex numbers, which are nothing but r times r, two-dimensional real plane, we used, or Hamilton used, these two definitions of addition and multiplication. This here is not surprising, simply component-wise addition, but here with the multiplication we have this somewhat strange rule, which incorporates exactly what we want to have in the complex numbers. For example, that 0, 1 times itself is minus 1, 0. Now, Hamilton, after a lot of trial and error, had the brilliant idea to repeat this process, but not to start with r, but with c, the complex numbers, and take c2, which today are called h in honor of Hamilton, for the Hamilton's quaternions. These are simply vectors, but now the entries are complex numbers. U and V are complex numbers. And on this set we again define two operations. Addition, exactly as before, simply component-wise addition, and multiplication, almost exactly the same, but for reasons we're going to see shortly, you need complex conjugation here. Here in this case I also could have written d overline, d bar, but in the real numbers this of course does nothing to the number d, but here this is very important to put the complex conjugation in the right spot. But apart from that, it is exactly the same process. And then Hamilton asked himself, well, is this again a field? The complex numbers are algebraically closed, meaning that it is impossible to have a field extension of the complex numbers. But the quaternions are a so-called skew-field. That means that all the field axioms hold except for commutativity of multiplication. This is where the word skew comes from. In German it's Schiefkörper. So now some notation and generalizations from the stuff we already know from the complex numbers. In print I would use boldface symbols, but on the blackboard this is not really possible, so I use this underline, which is a bit awkward because I also use the overline or the bar for conjugation, but what can you do? So if Q underline is a quaternion consisting of this vector with two complex entries, then I define its conjugate, the quaternionic conjugate, as here U bar, the complex conjugate, and here minus V, the negative of this complex number. And with this notation we have almost the same formulas as in the complex numbers. Because, and this is stuff that you should check on your own, yeah, I'm not providing any details here. If you multiply the quaternion with its quaternionic conjugate, you get the same as when you reverse the order, which is not clear because, again, the multiplication is not commutative, but either way you get this expression. The absolute value of this complex number squared plus the absolute value of this complex number squared, and the second entry is 0. And this guy up here we're defining as the quaternionic absolute value squared. So the quaternionic absolute value of this vector is exactly this real number. Okay, it's a real number. And then if I have any quaternion that is not equal to 0, so 0, 0 as a vector, then it has an inverse. It must have an inverse because we have a field, a skew field, but still inverses must exist. And this is exactly the same formula as in the complex numbers. But of course here I take the quaternionic conjugate as defined above and divide this vector by the absolute value of the quaternionic number. And this means of course dividing each entry by this real number. Yeah, this is just a real number. And then you should check that this indeed satisfies that q times q to the minus 1 is 1, 0, the neutral element of the quaternions. Please do that on your own. And as with complex numbers, this is rather awkward to work with, this vector notation. So there was a Cartesian form of complex numbers. In the same way, there's a Cartesian form. I don't know if it's called that in the quaternions, but I use this term here. Now, in the complex numbers, we had one so-called imaginary unit, the vector I. In the quaternions, I can define 3 imaginary units. First of all, one underline is the multiplicative neutral element 1, 0, as I mentioned above. And now for the 3 imaginary units. I bar, the quaternionic I, is complex I, 0. This is a quaternion, this is a complex number. Please be aware of the difference. J underline is just 0, 1, the 1 of the complex numbers. And K underline is 0I, again here I in the complex numbers. And then also check that, but this is pretty easy if you remember that every complex number can be written as A plus BI. Then you should be able to show that every quaternion can be expressed like this and that even this expression is unique. So I can write every quaternion using the 3 new imaginary quaternionic units and the 1. And this means as vector spaces, the quaternions are nothing but R to the 4, 4-dimensional real vector space, which is not surprising because after all it's C2, which is a 4-dimensional vector space over the real numbers. And here this quaternionic absolute value can be expressed as a squared plus b squared plus c squared plus d squared, generalizing the complex absolute value. And of course the complex numbers are part of the quaternions, as the real numbers are part of the complex numbers. And then using here this Cartesian form, we get this expression for the quaternionic inverse. I have here this quaternion, so I take minus signs everywhere except for here, and divide this by the square of the quaternionic absolute value, which is nothing but this number. And then I have a neat expression how to calculate inverses in the quaternions. And now here the famous and very important relations between the 3 imaginary units in the quaternions. Hamilton found out that I underline squared equals j underline squared equals k underline squared. And this is minus 1. This is the reason why they are called imaginary units in the quaternions. So same as in the complex numbers, I squared there is minus 1 here. These 3 quaternionic imaginary units squared give you minus 1, and also their product is minus 1. And then this easily shows that the quaternions are not commutative. So they are a skew field. Ij is not the same as ji, but here I get this minus sign. And ij is the same as k. And using these relations you can do almost all the calculations you need to do using here this Cartesian form when dealing with quaternions. And when Hamilton found out, when he found these relations, maybe on a walk he took, he was so excited that he used his knife, his pocket knife, and carved them into the what he called Brougham Bridge. Today I think it's called Broom Bridge in Dublin. And there is today a plaque telling you about Hamilton's famous discovery. And as I said, he tried many months or even years, I'm not sure. First of all, when he invented the complex numbers, he thought, well, maybe the same procedure is possible for R to the 3-dimensional space. And he tried and tried and tried. And there's an anecdote that he once came down to breakfast and his son asked him, Daddy, can you multiply triplets, which means 3-dimensional vectors? And Hamilton sadly shook his head and said, well, no, son, I can only add and subtract them. I cannot multiply them. So he was very, very excited when he took another dimension and found out that in 4 dimensions it is possible to define a multiplication that is almost the same as on the complex numbers except for non-commutativity. Today, when you study math in the first semester, it's possible to show that it's impossible to define such a structure on r to the 3 or in general r to any odd number. But Hamilton didn't know this at that time, otherwise he wouldn't have tried it for so long. You only need a little linear algebra and I think it's called mean value theorem, that every polynomial of odd degree has a 0. Using this you can easily construct a contradiction if you assume that there would be a skew-field structure or even field structure on any vector space of odd dimension over the reals. So after Hamilton had discovered this, he developed a very unhealthy obsession with the Quaternions and thought that everything in math and physics could be explained using Quaternions. And there were classes at the University of Dublin solely devoted to the study of Quaternions. And I think every math or science student had to take these classes. Hamilton wrote a lot of papers and books. Actually, you can find online his lectures on Quaternions, which is about 900 pages. This is just the tip of the iceberg. He did much, much more, but you should take a look at this work. And I think he went a little mad over the Quaternions and had the hope that, well, everything in the future would use Quaternions. And Lord Kelvin, the famous physicist and mathematician, once said, Quaternions came from Hamilton after his really good work had been done, and, though beautifully ingenious, have been an unmixed evil to those who have touched them in any way. So he recommended not to use Quaternions at all. Today we must say they are used, for example, in computer graphics. There's a neat way to describe rotations using Quaternions, which is much easier to program or runs much more stable if you program it than using matrices. This is one major application, and also in control theory and dynamical systems Quaternions are used. There's quaternionic analysis and quaternionic vector bundles and stuff like that, but the overall importance of the Quaternions was highly overrated by Hamilton. We have to say that. So it's not the revolution he had hoped for. Another interesting fact is, if you have seen this and this, you might think, well, then why don't I take just h to the 2, so c to the 4 or r to the 8, and this actually works. What you end up with are the so-called Cayley numbers, or here the symbol O for octonions. Octonions because of 8, and here the Quaternions because of the 4, r to the 4. And you can do this process actually infinitely long. This is called the Cayley-Dickson process. You mimic here this multiplication, but you have to be very careful because here in the Quaternions you have lost commutativity. So the order of the elements here is very important. And the correct way to do it is to take the product like that. So here you have to be careful. And here you have to be very careful where to put the quaternionic conjugate, and you have to be careful about the order of the factors. And if you do it like that, the problem is in every step you take, you lose important algebraic properties. Here, from here to there, we lost commutativity of multiplication. Here you even lose associativity. This is no longer an associative multiplication. Nowadays this is called an alternative algebra. You can still do calculations, but losing the associative law is very, very hard. And if you continue this process, you lose more and more algebraic properties, and at some point it's no longer useful, the structure you obtain. But interestingly, these Cayley numbers or octonions are actually used in string theory. This is not so surprising because I think string theory uses everything that exists in math. Not that I would know any details. And in other far-out mysteries like quantum logic or black hole entropy, so places where you wouldn't expect this strange algebraic construct, it is actually used in physics. Same with the Quaternions. Like in the 1930s, it was already clear that they could be used to describe the spin of an electron, which was a very important quantum mechanical property of the electron. So even then, people thought, well, now the Quaternions, they must really mean something or do something for me. But turned out they really didn't. Okay, I got a little carried away, but I hope it was interesting nonetheless. Thanks for watching, and hopefully I'll see you soon.